So what I want to talk about today is just one lecture on generative models for music, right? So far we've focused basically exclusively on images and with a detour into text, but what about other stuff, right? And so that's kind of what the rest of this class is going to be about, is generative models for blank. And so the first blank I want to fill in is music. And so there's been a small, I would say, but healthy community working on making generative music. And I just kind of want to overview that area of research today. So generative models for music. And so in a way, it seems like music should be easier, right? So a music, if you think about what music is, it's like a one-dimensional signal, right? And so everything we've talked about so far has been two-dimensional, so it seems like one dimension should be easier than two dimensions, right? But there are a lot of things about music that make it different and challenging compared to just like generalizing image stuff to one-dimensional signals, right? So, why is it different? Well, there are several reasons, right? One is that music has an extremely high bit rate. So, I know it's like archaic to say CD quality music, but certainly high quality digital music is basically like 44 kilohertz, right? That's what CD audio quality is. And also, a large number of levels. So basically, 16-bit audio is like standard high quality, right? So if you think about a 4-minute audio track at this quality, it's already 10 million samples, right? And these image generation things are really operating at the level of like 1024 by 1024, which is like a million pixel values, right? And then one thing to think about is that each of the samples is basically twice as many bits as like a typical single pixel. Well, I guess you could argue the images are 24 bits, but still, we're talking about like basically high bit rate, and also the speed. Well, I guess there's no sense of talking about speed and image, but the amount of data that you need just for even a short video or audio clip is surprisingly high, right? Another thing that is a big difference is basically that instruments can play chords, right? And we'll talk about different ways of representing music, but multiple notes at a time. So in a way, kind of like the analogy to images is that each pixel could be having multiple colors at the same time, right? Which is kind of a strange way to think about things, right? So if I was going to model, a pixel at different color levels, it'd be like saying, well, what if I could have like 3 color levels at once for a given pixel in a sense of music, right? And also, there's this kind of notion as we move into like more like songs, depending on how I want to model things, songs can have several instruments, right? So I could have, and then these instruments could be playing at different rates, right? So I could have like a slow saxophone and a high, rate of drums and stuff like that. So, there's kind of multiple voices at different rates. And the other thing is there are very long time scales, right? So we talked about attention for sure when we're talking about trying to make a coherent text, fragment, which you guys all discovered on homework 3. But if you think about music, right? If I'm thinking about like a, classical piece of music that's 15 minutes long, I have to be paying attention to stuff that happened like, 10 minutes ago to kind of come back to bring the original theme back into the performance. And that 10 minutes ago, if I think about how many samples that is probably like hundreds of thousands or millions of samples, right? And current models for attention are not really made to look back like that far, right? And I can't possibly maintain attention over like a million symbols. Well, I guess I say that. That's not typical to do in the models we talked about so far, right? And so there are lots of different ways to model music that kind of, some of these issues can be addressed. And that's kind of what I want to talk about is different ways of modeling and then different techniques that people have brought to bear on the problem, right? So the very first kind of approach to music took kind of like a very simple idea of just like notes that have discrete frequencies and discrete durations, right? So basically techniques range from basically, single, a single voice, right? One instrument at a time, and I could model like the note and duration for each of these things, goes all the way to basically, raw audio, where I don't model, notes or voices at all. I just model samples, right? And so if any of you have ever heard of MIDI, right? MIDI is like this digital audio format that when I was a kid looking at my Commodore 64 and kind of seeing MIDI files for music, that's like the simplest way of representing music, and it sounds like a computer, right? But of course, these days, it's possible for computers to represent whole music tracks just with raw audio, right? And so there are some key players in the field, right? So one is Google has a team called Magenta that is a key player. Facebook has a team, or Meta has a team called Audiocraft. And of course, OpenAI is playing in this field too. And of course, there are other kind of independent researchers, but in terms of corporate, those are the big three groups. And we're going to be talking about things that these groups have done over the past few years. And so many of the same ideas that we talked about from the very beginning, VAEs, GANs, transformers, diffusion, all that has been applied to making music as well. And so let me just preface this by saying that I'm focusing today specifically on music, right? So you could talk about generative modeling for audio in general. There's a huge literature on modeling human voice, right? Or modeling like sound effects like, traffic or ducks or whatever, right? So I don't want to talk about those things too specifically today. Voice in particular is like a massive thing. And of course, we've seen all this kind of like generative, voice cloning and stuff like that. That's not what today's lecture is about. Okay, so let's start with the simplest thing, which is basically like a symbolic, discrete representation of music, right? So that's where kind of a lot of research here started. So, one thing that I could do is, again, I can't teach you music theory in, an hour and still have the lecture, right? So hopefully you know that music is played at different frequencies, and in Western music we have this kind of like 12-note scale, and then we have octaves. Like, so if you see a piano, there's kind of like this repetition of these 12 notes as you go up the left side to the right side of the piano, right? So we could model, kind of like one note at a time as a series of basically notes and durations, right? So I could have, B3, 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 A3. So these indications are basically like, this part is, one of 12 possibilities, and this part in terms of octaves is probably one of, say, 8 possibilities, right? So, B3 is lower and B5 is higher, the same note a couple octaves up, right? And so these are like notes, and these are like octaves. And then for each of these notes, I could have a duration measured in basically, again, if you know musical notation, there's something called, the time signature, which kind of tells us in general how fast we're playing the song. And then this is like what's called a whole note, which is saying that this note takes up the whole bar of, the whole measure. Again, I can't teach you music theory from scratch. Basically, just think about this as like, it's not exactly seconds, but it could be construed as seconds if you normalize the scale of the music, right? So this is like a whole note. This is like, quarter note. And probably you wouldn't want to go any lower than like 16th notes, right? So certainly if you look at like crazy musical scores, there is some music like Flight of the Bumblebee that's like super fast, right? So, you can't necessarily go all the way down to like 64th notes or something like that. You probably want to have some sort of place where you stop in terms of discrete notes. And so you look at this, and you can immediately see that this kind of looks like a sequence of tokens, right? Very similar to how we talked about text, right? So it's not very hard to imagine that I could like kind of tokenize this, and I could produce a model that will generate kind of like note, comma, duration predictions based on a bunch of training data, right? Another way of thinking about how I could model these discrete notes is instead of directly specifying durations, what I could do is I could say, again, I have a whole bunch of possibilities here. So another way I could think about this is to say, or, I could have a list of note possibilities, which again is like the different octaves of the notes. Say I have 128 possibilities, for example. And then I also have kind of like, note on, and then, one note off token. And maybe like a rest token. So in this world, it's kind of like saying, I specify the note and I have a kind of like assumption that I'm kind of clicking through time steps of my music that I'm creating, and I just tell you, okay, so I'm turning this note on, it stays on until further notice, until I turn it off, and then if I don't want to play another note immediately, I can put it in a rest, or I can turn on another note. Again, this really only works for one note at a time, right? And so MIDI is this digital music format that can be used to collect or generate this type of training data. Because MIDI has been around for years and years and years. And lots of people have converted stuff into MIDI. And so let's go back to okay, so before diffusion models and so on, the very first thing we talked about was VAEs, right? And so Magenta was one of the first people to kind of try out a VAE for music, right? So one of the first things I want to talk about is basically something called music VAE. This was by Magenta. And again, it seems like a long time ago, but it was only 2018. And so this is like an autoencoder, very similar to what we talked about in class. And I think that you can probably kind of think about how you could apply this kind of encoder-decoder structure to this type of data. So one thing that we didn't talk about a whole lot in this class, and in some sense it's a little bit too late to go back and start now, but these encoder and decoder structures were both types of what are called RNNs, recursive neural networks. RNNs are basically a way of talking about kind of temporal, one-dimensional temporal data. And so if you know what an LSTM is, it's kind of similar to that. And so the idea is that we map an input X. And so here, this could be 2 or 16 bars of music, which would correspond to 32 or 256 samples. And so these are the little vectors I'm trying to encode into the latent space. And then the decoder is basically something that goes from this latent code back to a subsequence that I can kind of concatenate together to get the full result, right? And so the main use of this kind of music VAE was initially the kind of stuff that we showed on homework 1, which is kind of interpolation between simple short samples of music, right? And you can do this kind of latent space vector arithmetic and so on. So this basically enabled the same kind of interpolation and latent space arithmetic that we already know about. So let me just show you some examples, or play you some examples, because we're doing music now, right? So let me go over here. And hopefully both in class and the audio will stay on the recording here. So blah, blah, latent spaces. We already know what latent spaces are because we learned that a long time ago, right? So here's kind of an example, and hopefully this will work. don't know why this isn't working. Let's reload it. So basically, it's given like kind of a starting point and an ending point, and it's kind of like interpolating these simple tones from start to finish, right, in a way that's somehow coherent. And then there's also like kind of a drum sample. So I think it's like the start and the finish, and then it kind of like interpolates between these two things. And again, these representations of drum loops are, again, things that you can imagine are very simple to represent kind of like symbolically, right? My understanding is there's a whole different kind of discrete taxonomy for drums than there is for notes, but apparently it's a well-known thing. So, I mean, it's a good proof of concept. It's not like you want to sit and listen to these drum beats. They did eventually turn it into a trio, right? So here's an example of doing this with 3 separate voices. And so here there's some stuff that shows that there's some interplay between the 3 different voices that they've learned: melody, bass, and drums, right? So again, this was like an early result. And then here is this little web app they made called the Beat Blender. My MIDI devices. I don't have any MIDI devices. All right, I don't need that. So here, this is, again, we know about interpolation, right? So the idea is that each of these 4 corners of the square is a different drum beat, and then using the VAE, we can interpolate between these different drum beats. So here are the 4 different corners. And then I can take this and I can draw a kind of a path through the kind of like effective latent space and interpolate these drum loops as I kind of go from one direction to the other. Let's see if we can speed this up. Let's get to some. So you kind of get the idea that eventually, you know, this thing starts to merge towards the pink sounding drum beat, right? So again, this was kind of like an early example. Now, of course, all this was kind of like pre-transformer, right, in some sense, right? And so one of the big issues is that since we know that music contains these long-range dependencies, we'd like to apply attention mechanisms to the generation of music, but you know, it's hard to do without thinking about the massive memory that you have to have in terms of going back to all these tokens, right? And so when transformers came out, both Magenta, in terms of what they defined as the music transformer, and OpenAI, with what they called MuseNet, you know, used transformers, and I believe this was in 2019, more or less. And so in both cases, the key thing that made the transformer work was, even though I had this huge number of samples, that I don't have to pay attention to every preceding element, right? If I have a 44 kilohertz thing just for the previous second of music, I'm not trying to design a 44,000, you know, attention vector just for that second of music, right? There needs to be a way to do what's called relative self-attention or sparse transformers to make sure that works. I'm going to show you a sketch of that in just a second. These were kind of like the innovations that made this work to enable attention to go, you know, very far back. So let's take a look at what these look and sound like. So one of them was called Magenta's music transformer. This is late 2018. And so here are some things that came out of that. I don't know why it's still loading. I guess the page is still loading for some reason. I guess while I'm letting this load, one thing that I'm going to say, oh, here we go. So it's already sounding, a lot better than the simple stuff we heard with the VAE, right? One thing that you're seeing here before I go on is this kind of like representation of the music itself is now clearly like polyphonic, meaning that I can have chords and multiple things going on at the same time. And this is actually very much like, what old player pianos used to make, right? So if you've ever seen like an old player piano, this is a piano roll that was from 1926. And so I think that the idea was that someone actually recorded this, and then you can play it back on a player piano. And so the structure of this is basically there's like a punch for every key. You even got the lyrics on the side there, right? So this kind of representation of music, if you have the kind of right decoder, which is the piano, right, it can already produce like very realistic sounding music, right? So in a way, this is like the early use of the latent space, right? Going from the original song to this simple piece of paper back to the piano, right, shows that it can be done with this extremely simple representation, right? Which is a kind of a cool way of thinking about like a autoencoder, right? And so you can see here that the music transformer is using a very similar kind of approach to how it represents the music. And if you look a little bit further down the page, they also have this kind of, where is it? I guess maybe I linked to it here. This listen to transformer thing here. So here you can kind of browse through the kinds of things that this transformer has made, and then also these pictures are kind of like AI generated versions of the music, like kind of someone was talking about algorithmically generated cover art. This is similar to that, right? And so you can listen to automatically created So again, this is purely synthetic music, right? So it's a MIDI file that is played back with a piano-like synthesizer, basically. If you look further down this page, you can see that actually someone liked one of these things so much that then he actually played it himself on a real piano, right? So they transcribed the music that was generated by the AI system. So, it's interesting to think about, like, are we approaching music that people actually want to play and listen to? If you look at the page, there's definitely a bunch of stuff that are considered as kind of like failure cases, right? So if you look at this, there are lots of like weird things that it creates that may not be the best, whereas the failure samples. I mean, it still sounds kind of like classical piano music, right? But also there's not like necessarily, in some of these apparently, a lot of kind of like consistency. And just for comparison, let's take a look at the OpenAI version of this, which was MuseNet. So again, similar to what you saw on homework 3, it's kind of like where they prompt the generator with the first chunk of music, and then they let it kind of continue. Yeah. That's all right. And here you can kind of see there's clearly like this repetition, so it's going back and generating, stuff that was referred to, multiple seconds ago, right? Not surprisingly, has no soul. Internet commenters are impossible to please, right? Again, this was around 2008. And then let me just say on my piece of paper that, kind of like a kind of piano roll representation for this kind of like, polyphonic music. And again, just to kind of sketch out what does that mean, it's like saying I have a kind of a continuously scrolling roll of paper, and I maybe have like 3 different voices, and each of these things is telling me like what is going on with each of these voices at every point in time, right? So time is kind of moving along this way, and so I could have like, right? And so you can imagine that, this is something you could encode into a pretty simple subsequence again, right? So I could say, what is A doing at time 1? What is B doing at time 1? What is C doing at time 1? What is A doing at time 2? And so on, right? So I can kind of turn this, polyphonic sequence into a single stream sequence, and then I can apply, transformers and all that stuff just the same as I did before. So it's kind of like a generalization to multiple streams. And so, this at the time was probably, I wouldn't say the last, but certainly that was the point where we kind of moved from note-based stuff to, we're going to move into like raw audio in a second. So kind of one honorable mention that's kind of like an intermediate representation is, for those of you that are taking DSP or know something about DSP, you should know about the Fourier transform, right? So if you think about how real instruments are producing sound, they do so via a physical thing. Like if you're blowing in a flute or if you're plucking a string, like a sound is characterized by the harmonics of a note, right? So harmonics are basically like these overtone frequencies that occur at multiples of the fundamental frequency. So if I look at this page for a second here. So, a signal or a note has time on one axis, and if I think about taking the Fourier transform of a short segment of that note, what I see is the lowest bar is probably the actual frequency of that note, and then I get these kinds of multiples of that note at multiples of that frequency that have different weights, or different heights, right? Different coefficients on these. And so the idea is that the way that these harmonics are weighted and the fall off of them over time is what really characterizes the sound of a clarinet or an oboe or a violin or what you have, right? And so the idea behind this paper, which was actually using GANs to synthesize music, was to do the synthesis in this kind of like spectrogram domain, where the idea was to synthesize the log magnitude of the frequency domain, and also you have to think about the phase, right? Because sound is not just pure cosines. You also think about like when do those cosines start and stop, and that means you have to consider phase, right? So those of you that took DSP should have learned all about magnitude and phase and so on, right? So refer back to DSP lectures if you're looking to learn more about that. So let me just say that this paper on GAN synth, so this was also from Magenta. The idea was the idea was less to model music as it was to model like realistic sounding instruments, right? So the idea was they collected a lot of single note sounds from different kinds of instruments and then used that as their training data to be able to generate reasonable sounds from instruments synthetically, right? So the idea was, the goal is to learn realistic sounding notes from different real instruments. So it's definitely going beyond like that MIDI sound with an emphasis on actually duplicating what instruments sound like, right? And this is characterized by the pattern of harmonics in the spectrogram. Which is basically like a short-time Fourier transform. And that, just to put it on paper, it's like saying that this is like the fundamental frequency, and then I have the second harmonic and the third harmonic and so on, and maybe these fall off at different rates. And so this is time, this is frequency. Each of these slices is like a short-term Fourier transform. And so also you have to remember to take into account the phase of when these things start and stop. And then the results of that, in terms of how it sounds, you get these things that actually sound pretty well like notes. And then you can do the same kind of thing of interpolating between instruments in different voices, right? So here's an example of taking a, input sequence. So the music itself is not being synthesized. What's being synthesized is interpolating the instrument that is making the sound, right? So here's an example. So you're kind of hearing every kind of 10 seconds or so, we're coming to a different instrument, and we're kind of smoothly interpolating through the latent space of the GAN to make realistic seeming instruments in the middle. So that's pretty interesting. And the details of how they deal with phase and so on are pretty interesting. And one thing that's also, I thought, worth noting is that we also need to have like new evaluations and new metrics for what constitutes a realistic result, right? So there's a question about like, is there a version of like inception distance, which we talked about for GANs, for music, right? And so they talk in some detail in their paper about how do they make a music version of like the Frichet inception distance, and how do they do user tests to tell who how is one result preferred over another result. Okay. All right. So all the stuff so far is kind of like in a more what I would say simplified music domain, right? The other thing that you can do is just like jump right to making a raw audio waveform, right? You don't model the instruments, you don't model the notes or the harmonics or anything like that. You just go right to making like a total waveform, and you see how that works, right? So then you have many fewer constraints, but also the stuff that you generate may not be as like kind of crisp and clean, right? So raw audio generation So kind of like the key paper in this field was not necessarily targeted at music initially, but they found that they could use it for music, was a paper called WaveNet, which came out of Google DeepMind in 2016. So the original focus of this paper, I think, was actually like text-to-speech, but then they realized that they could actually make kind of like unconditioned music using the same kind of approach that they created, right? So the underlying architecture of WaveNet is this deep convolutional neural network, but the major insight that they had was, again, to deal with the same kind of issue of having to look back very far in the data set, they introduced something called dilated convolutions, right? So the underlying approach was to predict, one sample at a time using a CNN. But again, thinking about the convolutions, the key insight was to use what are called dilated convolutions. So if the idea is that my input is like, let's just illustrate like I have maybe, like this is my input sequence. And let's suppose, just for illustration, I'm using like convolutions of length 2, more or less. What I could do is I could say, okay, I have a hidden layer above this guy. And in the first hidden layer, I'm going to just take like pairs of these guys. And in the second hidden layer, I'm going to take, pairs of what I created. So now I'm going to kind of like make a structure like this. So effectively, what I'm doing is making convolutions that have mostly 0 elements that I don't have to bother to actually store. And actually, I should scrap this. I don't even have these intermediate guys. It's like saying then I go up to here, and then I go up to here, right? So it's like an exponential decrease in the number of elements that I'm leveraging from the previous layer. And so this means that the convolution has very low cost because I'm only using a couple of non-zero elements in every layer, but I can also look back very far in my sequence with only a few layers, right? That was kind of like the insight. So this was one thing that they used to deal with the massive sample rate of raw audio. The other thing that they noticed, or that they proposed, was that to deal with the 16 bits of audio that they generate, they use what's called a compander. So there's something called a compander, which is kind of like a non-uniform quantization. So again, if you've ever done DSP, you maybe have heard the word compander, which stands for compressor expander. So the idea is that instead of using an equal number of quantization levels, like for example, if we look at the quantization levels that we use for RGB images, we have 8 bits, and those 8 bits are evenly distributed between 0 and 255, right? The idea behind a compander is that we have maybe still only 8 bits, but then we spread those out over 16, 2 to the 16th actual levels, but the spacing is uneven, right? So I have maybe more bits at the high frequencies than I have at the low frequencies. And so the way in which these are nonlinear distributed follows this kind of power law called the mu law. And so again, this is something that's pretty well known in audio processing, but it makes a lot of sense to use here. And then they later used the same kind of idea. So this was basically like CNN. There was a VQ VAE-based method that they used. And I think I have a picture of WaveNet here. Let me just check. WaveNet. I actually had to go back to the archive to find this WaveNet. I don't know why they took it offline. So this is like a cached version. What's going on? WaveNet. And again, actually, it's pretty interesting to go back and think about the history of this, because there's a lot of, here, this is probably a better illustration than I could show before, right? So kind of we're generating the current output by this kind of hierarchical situation. Again, this is mostly about speech synthesis, but kind of like, this is kind of like an example of if you condition on speech, then you get. Hopefully that made some sense, I don't know. But of course, all of the customer service agents and so on that you hear on the phone are probably like, synthetically generated things. If you don't condition on actual text, then you can get something that kind of sounds like speech. So to me, this sounds kind of similar, but to you, it probably sounds like gibberish, right? But then the idea was that you could apply this to music, and the music that it generated is okay. So basically just applied to training it with classical piano music, it comes out with this raw audio generation. And the difference between this and what we talked about before is that there's no notion of notes or durations. It's just generating this file sample by sample, right? And arguably, it sounds kind of similar to other stuff. It doesn't necessarily have the same kind of like, long-term temporal coherence, but that was kind of like the beginning of thinking about, the raw audio. Then another development that came soon after that was from OpenAI again, called Jukebox. This was in 2020. This used a combination of like a VQ VAE, which we talked about early on, and also there's another transformer under the hood to make raw audio plus lyrics, right? So the idea was that you could kind of like condition the raw audio on some output that came out of GPT, because this is the same company that makes GPT, right? And so then the idea was that you could generate actual songs that had both music and AI-generated lyrics. So let's take a look at some of those results, which again, at the time they came out, were a lot of fun to listen to. So this is OpenAI's Jukebox. So you could do like, country song in the style of Alan Jackson, who's a country singer. So it's actually generating, lyrics and music as raw audio, right? I thought there was a version of this. There's a Katy Perry one. I don't know about that one. So you can kind of fool around. I could have sworn that when I looked at this last time, there was a thing where you could see the lyrics in the interface, but maybe it was a different thing I'm looking at. This could be better, maybe. So you can look at like a zillion samples on their webpage where some of it is just like kind of unconditioned on lyrics and some of it is conditioned on lyrics that come out of ChatGPT. And so, again, it's kind of fun to listen to. So next on my list is something that maybe you heard of recently. So this paper called Refusion. Actually, I don't think it was even a paper. I think it was just a project by these two guys, Forsgren and Martiros. So this was in 2022. And somewhat hilariously, all they did was feed spectrograms into stable diffusion, and it worked, right? So if you look at their, so again, this is unfortunately a cached web page, because when I went to refusion.org yesterday, it was down. Because I think these guys recently just sold their company to someone else, so I think that they've been hugged by the internet. So again, we all know about stable diffusion. The same thing is applied just to generating from a text prompt. You generate the spectrogram, and miraculously, it actually works, right? Unfortunately, I don't think these audio samples work on the Wayback Machine, but I think I can find examples from somewhere else. So let's just take a look. So here's a, so the prompt is basically funky synth solo, 90s rap, and it makes this short chunk. I thought there was a better example that I found yesterday. Where is it? This didn't work yesterday. We'll see if it works today. These are just samples here. Loading. Try it. There was one I found yesterday that was actually pretty good. Here, lo-fi beat for the holidays. Yeah, why does this not work anymore? Yeah. Yeah, those are the two guys who did it. Let's try this. So basically, they just kept on generating these spectrograms and concatenating them together to make longer sequences. I heard a good one yesterday. Actually, maybe I should just look under this for Refusion and see what we can find. Stable Refusion. These are all like React videos to Refusion. All right, I feel like none of these are actually the source of Refusion, so I don't want to give these people like random clicks. But it is a pretty clever idea. And so the cool thing was that in addition to generating the image of the spectrogram directly and just playing it like a spectrogram, they could enable all of the other stuff that we already know how to do with Stable Diffusion. Like they could do in-painting, they could do negative prompts, they could do image to image where you take an existing spectrogram and then make it look like some other thing with a text prompt that conditions it on the style. And so basically, this is just like Stable Diffusion to generate spectrograms. And like I said, for someone who knows anything about music, the hilarious thing is that it actually worked pretty well, right? And so this enables all this stuff like in-painting, image to image, stuff like we talked about last time, negative prompts. I mean, the thing to show you would be their Refusion website, but I feel like for whatever reason, Refusion's website is down. Try one more time. Nope. I know you can't see what I'm typing. It's all right. Yes, I feel like it's been hugged to death by the internet. Because like I said, it was just this past month that they were acquired by some big company. I don't remember which one. So, what? Yep. Oh. So yeah, I mean, it wasn't like totally automatic. There were a bunch of clever tricks to make this work, but it didn't take like a whole lot of effort beyond. I mean, it took some effort, but like it was a kind of a hobby project based on Stable Diffusion. And again, this is one of the things that like, I'm sure that when Stable Diffusion came out, no one was imagining that you could do this with it, and then people took off and used it, right? So in some sense, this is like the value of open source code that people can do stuff with it. So maybe this is one of the kind of like social good things. Unfortunately, yes, when I go to Refusion, I get timeout error. So, but it is cool. And the last thing I want to mention in this world is Audiocraft, right? So just recently, this year, was this big announcement from Facebook called Audiocraft. I guess it's meta, technically. So this is like a whole suite of tools. It's not really like one algorithm for generating music. And it kind of combines many things that we talked about. Like there are autoencoders, there's GANs, there's transformers, there's vector quantization, there's STFTs, there's diffusion. There's just like lots of stuff into this big like billion parameter system. But the results are also pretty startling. So like this came out just recently, Audiocraft. Yeah, this was in August. And so they have several modules, right? So there's a music generation, a generic audio thing. They trained it with curated and licensed music that they had collected. So again, this kind of comes back to where do you get the training data? A lot of this early work was basically on like classical music, which was out of copyright and so on. Here, I think Facebook trained this on music that they specifically gathered for the purpose. And so the results are, again, pretty good. So they do it, they do all sorts of stuff besides music. Here's the music. And again, this is basically a prompt, pop dance track with catchy melodies, tropical percussions, and upbeat rhythms, perfect for the beach, right? So that's the input, and this is what comes out, right? And then you could say, earthy tones, environmentally conscious, ukulele-infused, harmonic, breezy, easygoing, gentle grooves. So again, you can imagine that maybe this kind of thing will be a option that could appear behind like your YouTube video where you want some sort of like generic like background music instead of like licensed kind of stock music. Now you can make some sort of AI generated music, right? But it also can do things like making just like sound effects. So here's like sirens and a humming engine approach and pass. Or whistling with wind blowing. And of course, there's all sorts of like speech recognition and speech stuff that goes into this too. And so again, you can listen to lots of details, read the papers. I mean, there's like, this is based on a whole bunch of papers. It's not just like one monolithic thing. But again, we can see that we are now on the approach of, I think that probably honestly, it's unlikely that the best performing models are going to be based on kind of like this note and duration and kind of model type of thing. I think now we're just basically in the world of raw audio synthesis, right? So, this is like the future, question mark. But, I could imagine that YouTube will probably start to integrate these like AI generated music samples based on, you can imagine something crazy like where you upload your video, the video is put through something like some sort of like clip-based description of what your video is about, and then it generates some audio for you that matches the mood of your video, right? That seems like it's very well within reach. And actually, I know that some of you guys are working on something similar. There are a couple of people who are talking about like kind of like, you make a text description, you make some music lyrics, that's what you guys are working on for your project, right? Then you make the album cover, then you make the music, right? So all this stuff is kind of coming together in an interesting multimodal way. Okay, so that's kind of like my whirlwind understanding of music generation. I think it's interesting because to do it well, you definitely have to understand something about the source domain, right? So like you can't just, well, except for even the Refusion guys had to understand something fundamental about Fourier transforms and so on to make this work on their stable diffusion thing. But you do have to kind of respect and understand the differences in modalities, right? And so just as a segue, so the next lecture we're going to have is going to be on generative modeling for 3D objects, right? And so just in a similar way, even though it seems like 3D objects are just a one dimension up from 2D images, there's a lot you have to think about in terms of how do you model a 3D object in the right way. And so kind of everything is not just a simple extension of pixel grids down to 1D and pixel grids up to 3D. There's definitely a bunch of stuff you have to think about in the transition. So let's see, any questions or comments about music that I can try to answer? No? No? Yes?
One thing that comes to mind for me is like a possible system where you have like a representation in musical notation, and then you have a prompt and some kind of transforming model that takes that like, musical notation and applies
right.
whatever kind of style.
Yeah, so basically the prompt is a text prompt and then the simple MIDI file, and then you say make it into this, right? Yeah, right. Or use this as a basis. I'm sure that thing probably already exists somewhere. I wouldn't be surprised, right? Where you say, here's this, simple thing that my kid made, turn into MIDI, say make it sound like a symphony orchestra, and then you get the raw audio, right? I think that's very, very feasible probably right now, I would guess.
So I'm thinking if you want to actually make music with this, you can't just single shot generate the whole thing based off of the prompt.
Well, I mean, yeah, I mean, you might want to have some sort of way to steer the music instead of just getting like whatever it comes out, right? And there's a question about like, how do you, just like with GANs, right? How do you disentangle the result to say, okay, I like the tropical steel drums here, but I don't like the ukulele. How can I kind of like keep that part and decouple that part, right? So one thing that I haven't really seen that much aside from like interpolation stuff is kind of like, how do you then edit the result in a way that is kind of semantically interesting, right? Yeah, so there's lots of things you could imagine, right? And even though there's a lot of music out there, it's also, I think, a tricky thing to curate the databases that you need to solve those kinds of problems, right? So there's still, I think, probably orders of magnitude less well-behaved music data to feed into your algorithm than there are images, right? And we're going to talk about the same thing for 3D. There's also like orders of magnitude less 3D information to train on, right? So images are kind of like the sweet spot where we have so many of them on the internet. And even though music has been around for much longer than digital images, it's also not, you know, quite as rich in terms of like how much you have, right? So yeah, it's an interesting question. Other comments or questions about music? All right, so hopefully that was interesting. I'm going to stop the video.